equation, that's an exercise for you guys. All right? So I want you to look at the way we proved Bellman's equation for dynamic programming and just think how we might apply this in the Markov decision processes case. Okay? You've learned enough stuff to be able to do that. Okay? So it's a good one for you to try out, and obviously we'll go through the proof of that in the tutorial, okay? Okay. Now let's go to exercise 5. Okay, so you're running a company or you're just a private seller and you've got a car, all right? You've got to sell the car, okay? And at every time from t equals to capital T minus 1, you set a price for the car, P of t, all right? And a customer comes to see the car, okay? Now, depending on which customer comes, there's a probability that the customer buys the car at that price P, okay, and the probability is D of P, where D means demand, all right? And if the car isn't sold by the end of time, capital T, then the car is sold at some fixed price, capital WT, okay? Your aim is to maximize the reward from selling the car. Okay. Now, what we're going to do is we're going to solve that problem. Okay. Find the recursion. Okay. Following our Bellman's equation, which I'll restate above. Okay. For the optimal reward, when the probability of selling the car is given by this 1 minus P of t. Okay. Right, so the higher I put up the price, the less the demand is going to be. Okay? The lower the price is, then the demand is going to be higher, or you're more likely to sell it, but then you don't make as much money. Okay? So this is a classic area. It's not really finance as such, but, well, it is sort of finance, but this is an area called revenue management. Okay, so a lot of companies use revenue management strategies, so aeroplane companies, car companies, a lot of big sellers, Amazons and all the rest of it, Alibabas will use revenue management, essentially determine prices that are going to maximize profit subject to demand. Okay. So, and again, if we want to solve that kind of problem, we're going to end up with a Markov decision process. So you've got a Markov decision process to solve. Okay. Right. So let's just recap above quickly the Bellman equation. So I'll just pass this. We should just read through it quickly. So the Bellman equation is exactly the same as before. The optimal reward, W of t, is given by maximizing over all the actions, okay, of the current reward plus the expected value of the future reward, okay? Plus the expected value of the future reward of the next data mat. Okay? And that was exactly what we were doing in this picture here. Okay? We're saying, well, if I'm here, I expect to make 3. You're not certain to make it, but you expect to make from this point. So you're inferring from this point the expected value of the path you're going to take to the optimal reward. Okay? Right. Okay. Right, so let's have a crack at this question. Okay, so we're going to let x of t be the state of the system, and the state is whether I've sold the car or not. Okay? So I'm going to let this be the indicator function. So I draw indicator functions like this. of the car is sold by time t. Okay? Oh, let me say not sold. I've done it with not sold here. So not sold the car by time t. Okay? So in other words, 0 means I've got no car. Right? So if x of t equals 0, then what is x of t plus 1? I've sold my car. So the next time, do I have a car or not? So no, I've sold it. I've got one car. So if at time t, I've sold my car, then at time t plus 1, I've sold my car. Okay? Right? So that's one entry of our plant equation. All right? Okay. Now, the more interesting one. I haven't sold my car. Okay. Then what's going to happen at time x of t plus 1? Okay. Well, either I sell it, okay, or I don't sell it, okay? And I sell it with probability what? Sorry? dp, yeah, perfect. dp of t. Where p of t is the price at time t, okay? Okay. We're going to let r of t of x of t be the reward from t to capital T given x of t. All right? We're going to let w of t, x of t be the optimal reward, again, from t to capital T. Given x of t. Okay? So one thing to note is that RT of 0, so given I've sold the car by time t, the reward I'm going to get in the future is going to be 0 because I've sold the car. Already made my money. Okay? 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 So the values that we're only interested in are the R of 1 and W1 values. Okay? Okay. Now, let's think about what happens to the rewards. Okay, so we're going to kind of rederive the Bellman's equation for this example. All right? So, let's suppose we're going to look at R of t minus s. Okay, so you've got s years to go. All right? And let's suppose you haven't sold the car. You've got a car, you've got s years to sell it. Otherwise, you're going to get a fixed price for it. Okay? And potentially lose money. All right? So, from this point until the next round, two things can happen in the next time unit. Either I sell the car or I don't sell the car. All right? So, what's the probability I sell the car? DP, yeah. Okay. And how much money do I get? Yeah, PT minus S. And then I should sum up all the potential future rewards I'm going to get in the future. Well, the next state I'm going to go to, if I've sold the car, what is the next state of X? Is equal to 1 means I've got a car, I've sold it, so it's, yeah, someone said it right, 0, okay? And what's this equal to? 0, because there's no more revenue to be made when I've sold the car, okay? All right, a little bit too much detail there, but it's worth writing out the way we formulate the other dynamic Markov decision processes, okay? So that's the case we sell the car. What about the case that I don't sell the car? Okay, with this probability I don't sell the car, all right? So if I don't sell the car in that day, how much money do I make that day? 0, yeah? And then, well, we can look at, given that that's happened, how much revenue am I expecting to make in the future from the next day? Well, it's R of t minus S plus 1, because we're 1 day forwards, okay? And do I have a car or not? Yes. So it's 1, okay? So notice I've got a recursion here, okay, where I relate the t minus s term to the t minus s plus 1 term, okay? So the same as before with the tree, we're kind of, this is like one peg further in the tree, and I can solve backwards with this recursion, okay? The only thing I haven't done is made the decisions as to what the prices should be, okay? So I haven't decided made the left or right decision at this point, okay? So, notice, so I'm kind of doing this proof for you as we go, but just with this example. So if I was going to make the optimal decisions from time t minus s plus 1, from this point onwards, okay, this wouldn't be R, it would be W. We use W for the optimal one, okay? So if we were optimal, okay, we would have here d of p of t minus s, p of t minus s, plus 1 minus d of p of t minus s, times, well, saying that we're going to make optimal decisions from time t minus s plus 1 onwards. So that would be w t minus s plus 1, 1. Okay. So given I don't sell the car and I'm going to make optimal decisions from there on out, okay, so let's say from tomorrow onwards I'm going to make the optimal decision, and this is my expected revenue, given that, what should I do to this, what should I do to this expression in order to determine my price? In order to maximize the revenue for today, and then from there on out. What do you think I should do? So I've got one variable here I can choose, which is the price that I advertise my car for today. And this is the revenue given the price. Okay, so this is how much money I'm making for price P. So what should I do to get that? Well, yeah, I've told you the answer. So what I should do here is maximize over P. All right? Okay? So my optimal choice is, given I'm making optimal choices from tomorrow onwards, is make the optimal choice for today, which is to maximize this expression over P. All right? That is exactly the same idea as this tree here, where I said, well, I'm assuming I'm going to go right here and make the optimal choice. Now, given that I know in the future I'm going to make the optimal choice from tomorrow onwards, let's say this is today, that's tomorrow, from tomorrow onwards I'm going to make the optimal choice and go here. So the optimal choice at this point is to go that way. All right? So it's the same principle. Okay? Right. So choosing P of t minus s optimally, we have the optimal value function is going to be the max over P of t minus s of this expression. Okay. So now I'm just going to make some substitutions. Okay. So notice at the beginning of the question I assumed that d of p had a specific form, 1 minus p. Okay. I'm gonna, and also just to make the notation a little bit more tidy, I'm going to call this guy c of t minus s, and I'm going to call that guy c of t minus s plus 1. So I'm just going to call it c because I don't need to write all these ones and stuff. Okay, and I can make the substitution in here that this is 1 minus p plus. Okay. So I can rewrite this whole expression as c of t minus s equals max over p of p 1 minus p plus. Okay, does everyone understand what I mean by 1 minus p plus here, just to make sure that... So I mean the positive part of this. So if this is negative, I take the answer to be 0. All right, and if it's positive, I just take that number. All right, okay. Then 1 minus p plus c of t minus s plus 1. Okay? Looks a little bit tidier now. All right? Same thing, it's just a bit tidier. Okay? What you'll notice is this function is something that I can differentiate. At least most of the time I can differentiate it. Okay? So I can solve. I can do differentiation with respect to p. For maximizing, I set it equal to 0, the derivative, and then I solve, okay, for the optimal choice of p. Okay, so differentiating over p gives, I'm not going to do the calculation for you, gives that p is equal to c of t minus s plus 1 divided by 2. Okay, I'll let you check that when you get home. All right. So one thing you can notice with this is substituting back in, we're going to get c of t minus s, okay, equal to 1 plus c of t minus s plus 1 divided by 2 squared. All right? So your optimal revenue of one time unit before is sort of the average of your optimal revenue between 1 and your optimal revenue, and then squared. Okay? In other words, what we've got is kind of a nice recursion here. Okay? You can notice, first of all, we can start with, well, firstly, we've now basically solved the problem, because I can start with the final price W of t, okay? So I start with my value C of t, whatever the money I'm going to get in the market at the end of time is, and I can just repeatedly substitute into this expression the value of C of t, it gives me the next one, and I substitute it back, it gives me the next one, I substitute it back, it gives me the next one, and I can calculate the optimal price for any number of years backwards. Okay? Does that make sense? Because what I do is I take, let's say this is 10, let's say this is, I don't know, a third, or something like this. I take a third, add 1 to it and divide by 2, square it, and that gives me the optimal revenue the year before, okay? And also through this, the optimal price that I should set it at, okay? And then I take that value, I plug it into here, and then I get the 2 years before optimal revenue, and also the optimal price, okay? And then I substitute in again, I get 4 years back, and the optimal price, okay? And I can just solve this backwards, okay? So, we can analyze this a little bit further. Firstly, we can notice that it's monotone, okay? I'm just going to draw a quick picture, okay, and then we'll be done. It's always good to draw a picture. So this is the line, if I've got C over here, and I've got a line C dash, okay, we know that in this expression C dash is 1 plus C divided by 2 squared, okay? I can draw that function on here. It looks like this. So there's 1, there's 0, and it starts at a quarter when C is equal to 0, okay? So what happens? So if I started at some value here at the beginning of time, so that, sorry, at the very last time, the amount of money I'm going to get in the market, okay, then effectively what we're going to do is we're substituting here, and that gives me the optimal revenue the next time, okay? And then I substitute here and I get the optimal revenue the next time, okay? So that would be like C of t minus 1, C of t minus 2, all the way up to 1. And it's just going to slowly increase up to 1, this function. Okay? Now why does that make sense? Well, if I know I'm going to make less than 1 on the final day of selling, but I've got a really long time, okay, I might as well set the price really high, because there's a lot of time for someone to come along who's got a demand that's close to 1. Okay? Because we're going to get people who are willing to accept the maximum price, which is 1 here. All right? Does that make sense? Because the most I can get out of the demand here is 1. Okay? So I might as well set my price really high so the probability here is really close to 0. So it's really unlikely I'm going to sell the car. But if I wait long enough, someone will come along and eventually pick it up. Okay? So we start with a high price, wait a while, and then slowly this function is going to navigate down to the final price that you're going to sell it for at the final time. Okay? So it gives you a rule by which you should set prices high, and then as you notice you're running out of time to sell something, you lower the prices. Okay? This is something that's used all the time, particularly like when you buy your airline tickets and all the rest of it. They're doing this. They're running Markov decision processes in the background, which are basically deciding I've got this many seats left. I'm going to have this many. The flight's going to leave at this time. Okay, I've got to sell them all. I'm going to vary the price in order to meet the demand and slowly bring this curve down to the final point. Okay. So this is something that's very commonly used by different companies in practice. Okay. So usually it isn't just one car, and there's different market effects and all sorts of other things going on, but the basic kind of under the hood algorithms that are used are kind of Markov decision processes. Okay? Right. Okay, and then next time we'll cover kind of a call option, how to use it for when we should exercise a call option. Okay? All right, thanks.